Okay, Mauro Oliveri and Luigi Blasi are going to speak on the first space qualified RISC-V
Okay,
microcontroller launch for a satellite.
thanks.
Good evening, everybody. I'm Luigi Blasi. I'm a PhD candidate from University of Rome and FPGA designer for the SI Aerospace Technology in Bremen. Today, with my colleague Francesco Vigli, we are going to present you the first space qualified Klessydra RISCV microcontroller to be launched on a satellite. The work has been developed by the Digital System Group Lab at the Sapienza University of Rome, which is led by Professor Mauro Olivieri. And here you can see a sketch of the whole group. This is the outline of our presentation. We start with the motivation of our work. We will analyze some space and environment issues, as well as some fault tolerance architectures. We will go deeply inside the Klessydra FX3X core family, and then we will finish with the results and the perspective of our work. So we have nanosatellites, such CubeSat, PicoSats, and PocketCube, which allow academic institutions and small companies to afford the space mission research, as well as the utilization of commercial off-the-shelf component, which can reduce the cost. Since the space-borne electronics will work in severe, extremely environment, a specialized microarchitecture is required in order to provide a high grade of reliability. So the question was, what about sending a RISC-V microcontroller in space? And we based our work on the roadmap traced by the PULP group at ETH of Zurich and University of Bologna, in particular on the Palpino platform. And here you can see a sketch of the platform. We concentrated our work on the core, and we developed several microcontroller cores targeting different features and applications. We introduced the multiple interleaving hearts on the T0 version and the vector accelerating support on the T1 version. And just for your knowledge, the T1 version will be discussed tomorrow on a poster. But today, we focus on the Klessydra FX core, which provides a fault tolerance support for space-qualified applications. The electronics which are going to be used in space are affected by the error and faults due to the effects of ionizing particle that interacts with electronics components. These are called single event effects, and here you can see a resume of the major types of single event effects. We can have the single event transient, which basically are spikes of current and or voltage in two different nodes, temporary, of a combinatorial logic. We can have also the single event upset, which are bit flips in sequential logic like flip-flops. And we can see, as well as we can be the multiple bit upset or cell upset in sequential logic, but basically RAM memories. We can have also some effects which are called CEFI, single event functional interrupt, which are caused by any combination of the previous one. And this can provide malfunction in our systems. So we need protection techniques to increase the fault tolerance of our system. And basically, the idea is to introduce the redundancy. The redundancy is a concept which means that we can duplicate components and modules, then perform the same operation or task or activities in all of them, and then check the result at the end. This will allow us to detect errors or maybe also correct errors. The spatial redundancy uses three kinds of approach, which are the double modular redundancy, which use two modules and perform error detection. If we use three modules, we use the triple modular redundancy. With a voting system, can both detect and correct errors. And also we can once we have detected an error, we can bring the system to a fail state using a fail state finish state machine in RTL design. The concept of temporal redundancy is similar to the previous one, but differs because we don't duplicate the hardware, but just use a repetition in time to perform error detection and at least also correction. Some techniques of checkpoint and recovery can be used at task level or cycle level. It depends on the granularity of the application. And we can also use miscellaneous techniques. We can use watchdog timers in some particular configuration as the windowed, and also EDAC protection from memory, so some kind of information protection. We analyzed many techniques, and we are going to analyze more with the goal of defining a subset of them that will be implemented on a prototype that will be launched on a satellite soon. And here you can see some of them we studied. We started with a full tripler modular redundancy on the hearth register file, on the CSR, and on the pipeline registers. Then we try also to reduce, to increase the, to decrease the area occupancy on just only a subset of register. We define a new approach using two pipelines which can execute the same task with a lockstep architecture and execution. We work on a temporal thread redundancy using a delay shadow thread with single pipeline, which basically perform 3 times the same operation and then check result at the end. Or we use the double thread shadow with double pipeline. We can also perform error detection and correction. Also, the idea of checkpoint to be set and restored before executing some critical task of our code was explored. Watchdog timer and watchdog heart, and also the memory ACC protection for all the memories. Now it's time to leave the floor to my colleague Francesco, which will go into you more details about the Klessydra architecture.
Can you hear me? Okay. So, the TX and FX Klessydra family share the same multi-heart pipeline principle scheme. Every heart has its own program counter, controller status register, and registers files. At each clock cycle, an instruction is fetched from a different program counter according to an interlevel multi-threading scheme. Also, an heart can send a software interrupt to another heart. Starting from this architecture, we started the study and the implementation of fault-tolerant techniques. The first technique that we applied is the TMR. Klessydra F03X is the TO3X core with all registers protected by TMR. Also, the pipeline implements fail-safe and fault-tolerant FSM. The architecture is characterized by the triple redundancy of most registers. Includes the registers that are already replicated for multi-threading support. In this way, the system can detect and correct an error in every part, in every critical part of the core. Control status register and program counter are also protected with TMR. Looking at the processing pipeline, we can clearly see that TMR technique applied in a multi-threading system results in a triplication of the resources that may be difficult to manage in a low-end FPGA for low-cost satellites. The F03X is also scalable. We can reduce the reliability of 1 or 2 hearts in order to save resources. The F13X implements double modular redundancy on the pipeline. The system can detect an error and automatically restore the core to a checkpoint. Dedicated hardware called checkpoint and restore unit control the system by checking the output of the pipeline stages in order to detect an error. Restoring the checkpoint can be managed by the user through 4 pseudo instructions. The CRU also has additional feature for the execution of dependent traits. The F13X and F43X microarchitecture differs only for the instruction processing unit. The 2 pipeline is loaded with the same instruction, and the output was checked before an error can have a side effect. The recovery procedure is managed by the processing unit as an exception condition. The checkpoint data are stored in a dedicated location inside the memory. The Klessydra F23X implements a time-space redundancy hybrid technique in order to obtain advantages of error correction and smaller increases in resources compared to the tribal redundancy. Each hard instruction is tripled. 2 replicas are elaborated simultaneously in the 2 pipeline, while a shadow copy is executed with 1 cycle of delay. The errors are corrected by the shadow control unit by majority vote. This core has its own microarchitecture. The shadow control unit manages all the system through different subunits. The shadow sinks unit handles the interleaved multi-pipe elaboration, controlling the output of the program counter and the instruction input of the 2 pipeline. The shadow voting and control manage all the voted output of the processing pipeline. The shadow register unit controls the input and the output of the 2 replicated register files banks. A group of tests have been executed to compare the performance between FX3X cores and TO3X core. As we can see in the table, the application of TMR technique in FO3X core does not reduce the performance in terms of clock cycles. Instead, the checkpoint in the F13X core and the time redundancy in F23X core have an impact on the performance. The target FPGA used for synthesis and implementation is the Xilinx RT7A35. To prevent the elimination by the optimization phase of the TMR register, it's necessary to activate the keep equivalent register option in the Vivado synthesis settings. As we can see, the impact on resources are dependent on what kind of protection we implement. In fact, the 2 cores that use an error correction technique are those that use more resources. To test the robustness to bit flip, we design a full injection test that can reach the upset rate up to 1 upset per millisecond. As we can see, the 2 techniques implemented in F23X and F03X are independent of the number or error rate. The F13X, in other hands, is highly dependent on the error rate and on how often the checkpoints are made. In conclusion, the Klessydra fault-tolerant FEX series provides great versatility and allows you to lower the cost of the hardware in a small satellite. At this moment, we are working on time redundancy technique derived from F1-3X and F2-3X core. Also, we are developing multi-trade watchdog timer and other software techniques. The final choice of the core version to be included in the final prototype is expected in early September. We are still working on it and testing other fault-tolerant techniques that we are studying. By the end of these years, the space-qualified Palpino Klessydra RISC-V platform is expected to fly in a sun-synchronous low-Earth orbit PotaCube satellite. Stay tuned to read the tweets it will send to the Earth. Thank you.